Okay, students. Now I'm going to continue the chapter. In the previous chapter, we discussed what upthrust is. I'm sure you all can understand what upthrust is. We did the activity. So you know, when we immerse an object partially or completely in a liquid, the liquid or the fluid exerts an upward thrust, an upward force. That is what we called as upthrust. And you all know, because of the upthrust, we see as the weight of the object is less than the weight of the object in air. That's why we call it the apparent weight. So you were able to understand all these concepts from the activity that we did in the previous chapter. So I'm going to continue from there, starting from the conclusion. I gave you the conclusion in the previous chapter also, but again to recall what we discussed. The conclusion that can be drawn from the result shown in the table above is that when the object is partially or fully submerged in water, the upward thrust acting on the object is equal to the weight of the water displaced by the object. So that is what we calculated. You all can remember, students. So when we calculated all the values, you were able to see that. The displaced water, when it was 0.3 Newton, the upthrust was also 0.3 Newton. When the upthrust is 0.6 Newton, when the object was completely submerged, the weight of water displaced was also 0.6 Newtons. So you understood all those concepts. So this is known as the Archimedes principle, as it was first introduced by the scientist Archimedes. So I told you all this also. He is the one who introduced the concept to us, and also after him only, we have to honor him only. We name the displacement jar as Eureka jar. So now, if we look at the Archimedes principle, this is what he introduced. When an object is partially or completely submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So the conclusion of the activity. When an object is partially or completely submerged in a fluid, we can say completely or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. So you all can remember that, students. If I recall what we discussed before, again and again I am showing you all the activity. So we had the object in water. So when it was partially submerged like that, there was water that was displaced. So here upthrust, and here weight of water displaced. So that is how we look at the upthrust. Upthrust is equal to weight of water displaced, or if it is any fluid, weight of the fluid displaced by that object. And that is what we say as the Archimedes principle. You all have to remember this principle, students. When an object is partially or fully submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. You all have to remember, students, it is the weight of the fluid that is displaced, not the volume. It is the weight of the fluid. Because weight is what we get in newtons and that is equal to upthrust. Both are forces. Is that clear to you? So why does an object displace water or displace a fluid? When you put an object into water or a fluid like this, when it goes in, obviously you all know there has to be a volume that has to be occupied by the object. And because of that, the liquid will rise. So depending on how the object gets immersed. Now we saw when the object was half immersed, the upthrust was 0.3 Newton. The weight of water displaced was 0.3 Newton. But when it was fully immersed, what happened? The upthrust became 0.6 Newton and the weight of the water displaced was also 0.6 Newton. At the same time, you were able to see that there was more water, more volume of water that was displaced. That is why the weight is also more. So, based on how the object is immersed in the fluid, there will be a certain amount of fluid that is displaced or a volume of fluid will be displaced. So, the weight of that fluid is that what is equal to upthrust. So, from this, we can understand how different objects float or sink. When floating also, whether they are partially submerged or they are completely submerged. Even when we say partially submerged, sometimes they are almost like floating on the surface. Only a small part of the object is within the fluid level. So like that, different objects float differently in fluids. And again, the same object can float or sink differently in different liquids. That is what we are going to understand now. So with that, I will move on to the next slide. The figure given below shows how three different objects A, B and C are submerged in water. So these are the three instances I told you. Now A, if you take A, what can you say there? A is partially submerged and floating. So this is partially submerged, and floating. What can you say to this? B. It is completely submerged and floating. Completely submerged and floating. See, now it has come down completely. It's sitting on the bottom surface of the container. So there it is sunk in water. Object sunk in water or sunk in water. Here I'll say water because in the above also submerged in water. So if it was any other fluid, you can say sunk in fluid. So the first two, A and B, they are floating. C is sunk in water. So A and B, you can see one is partially submerged, the other one is completely submerged. In all three instances, there will be the upthrust exerted by the water. So in all three instances, you will see the upthrust exerted. I'll put it as UA. Here the upthrust will be UB. Here also there will be an upthrust that is going to be UC. But the way the upthrust is exerted by the water on each of these objects is different. That is why they are in different positions. So again, something similar to what you have learnt with forces, students. You all know weight is a force that is acting downwards. Upthrust is a force that is acting upwards. So when they are equal and opposite, there is equilibrium. So if it is partially submerged and floating, still there is equilibrium between upthrust and the weight. Here completely submerged and floating also, same thing. But if it is not in equilibrium, of course, then there is a difference. we will try to understand the relationship between upthrust and the weight in all three instances, whether they are equal or different. So here, what I explained to you all, object A is partially submerged and floating, while object B is fully submerged and floating. Object C is fully submerged and resting at the bottom of the container. Can you think of the reason for this difference? So now we are trying to understand the reason. That is what I said, the relationship between upthrust and weight. Weight is acting downwards, upthrust is acting upwards. Already you all know upthrust is equal to the weight of the liquid or the fluid displaced. Those are the things you already know. Now we will establish a relationship between these components. So engage in the following activity in order to understand it. So then we will look at the activity now. Activity. You will need 3 objects of different materials. Here of course students, you can use 3 objects of different materials. An object that can float partially submerged, float completely submerged and sink in the liquid, or here it's going to be water. Or else what we can do is we can take the same identical bottles. You can take glass bottles, 3 glass bottles and fill sand. You can have just the bottle 1 half filled with sand or 3/4 filled with sand, so that you can make it to float and sink as necessary. Or else you can even fill it with a liquid. So you can change the weight and you can bring it to all these 3 different positions. So either 3 different objects or the same bottle filled with different substances or the same substance to different levels. Either way, what you need is 3 different objects similar to A, B and C. They have to be similar to A, B and C when they are put into water. So you will need 3 objects of different materials. One of them, A, should float in water. That's important. Partially submerged. Then another one, B, should float on water fully submerged. So first one has to be partially submerged. The second one has to be fully submerged. So this is partially submerged. This is fully submerged. Such an object could be obtained by filling an appropriate quantity of sand into a bottle that could be properly closed. So as I told you all, you can fill sand, you can fill water, anything is fine. The third object, C, should sink in water. So the third one should sink in water. Measure the weights of the 3 objects, A, B and C. So here you are going to measure the weight of the object in air. Why? You need to know the real weight. You need to get the apparent weight. Then only you can find the upthrust and also you can establish a relationship. Now measure the apparent weights of the 3 objects while A is floating, partially submerged, B is floating, fully submerged and C is sunk. So when we say measure, now you have a beaker with water. We don't have to do all 3 at the same time. We can do it one after the other. So first what I will do is I will take A, attach it to the Newton spring balance or spring balance, get the weight in air. Then I will let it to float like that. So there you have to be careful students. You shouldn't be pulling the object up or you shouldn't be pushing it down. You should allow it to float and at the same time the string has to be straight, not loose. So then you will get the weight when it is floating. So before that, to see and confirm that it is partially floating, you can only put the object in without the thread or without the spring balance. So you know it is partially submerged and floating. So you take the weight in air, then weight when it is partially submerged and floating. Then you take object B. Again you get the weight of the object in air. After that, you put it into water to confirm that is completely submerged and floating. Then you take the weight of the object while it is completely submerged and floating. That is object B. Then C again, you take the weight of object C when it is in air, put it into water to confirm that it completely sinks in water. Thereafter, you can get the reading. So, you will need to take 3 sets of readings. For objects A, B and C, one in air, one when it is partially or completely submerged in water. Is that clear to you? So, that is the method of the activity. Now, let us go to the lab and do this activity. Thereafter, we will fill the data into the table that is given to you. Okay, students. So, from the previous activity and the Archimedes principle, you all know that when an object is partially or completely immersed in a liquid, there is an upthrust exerted by the liquid. Due to the upthrust, there is a weight loss that is observed, and the weight that is observed when the object is immersed in a liquid is called the apparent weight. So, now what we are trying to do is, if we take different objects, if we put them into water, here the liquid is water, so when you put them into water, they float in different ways. There can be an object that sinks in water. Then there can be an object that floats partially submerged in water. Another object floats completely submerged in water. Now we are trying to understand the reason behind this. So to do that only, we need these materials. So as I did before, I am going to use a stand to fix the Newton balance so that it's easy for us to get the reading. Here I have a tank with water, a glass tank with water. And for the objects, now you all can either take bottles filled with sand to different levels. Here I have filled water to different levels. So that one will sink in water, the other one it will float completely submerged in water. The other one, it will float partially submerged in water. And also it's colored water so that you can easily understand and identify the objects. So first, if I show you all, now although I am going to hold on to the thread, I will not be exerting a force after I put it into water. So here you can see once I put it into water, I am just holding it loose. So you can see the object floats in water, partially submerged in it. The same way, if I take this bottle, here you can see this is the object that floats completely submerged in water. The second type of object. Then we have the third object, the bottle filled completely with water. You will see if I keep on letting it, it will go down. So it sinks in water. So we have all 3 objects. Now I need to dry the outer surface so that I can take the weight of the objects. I will take the first object that will float partially submerged in water. So here if we take the weight of the object, you all can see there. So you can see the reading, students, it's 1.5 Newton. Can you all see the reading? So 1.5 Newton. Now what I am going to do is I am going to immerse it in water. So for that I will hang it in this stand. Now can you all see the reading? It has come to 0. Now it is partially submerged and floating in water, and at that time you can see the reading of the Newton balance 0. So that is what I need to enter here. So here initially the weight of the object was 1.5 Newton. Then the apparent weight, that is 0, and it is partially submerged. partially submerged in water. So when we write as partially submerged, it's understood it's floating in water. So that is the first object. Initial weight, that is the weight of object in air, was 1.5 Newton. Apparent weight, you can see the reading, it's 0 Newton. And also the object is partially submerged and floating. So the second object, again you can see the weight. So here you all can see the reading of the Newton balance, 1.8 Newtons. The weight is 1.8 Newtons. Now again we will have to connect it here and I will let it to float, completely submerged in water. So here you can see we needed to bring the stand also down so that the thread is loose, so that there is no force exerted by the Newton balance, because it is completely submerged and floating in water. You all can see the reading, students. It is 0. Now the thread is straight, twine is straight, and the object is floating completely submerged in water. You can see the reading. The Newton balance reading is 0. So here the weight of the object was 1.8 Newton and the apparent weight is 0. So here it is completely submerged. Completely submerged in water. Then we have the next one. The third object, it's here. You can see the weight of the object as 2.5 Newton. Weight of the object is 2.5 Newton. So then if we immerse it into water, you will see, students, it will go down. There is a reading. Can you all see now? It is 0.5 Newtons. Can you all see the reading? 0.5 Newton. Okay, students. So we got the readings. Weight of the object was 2.5 Newton and you saw that there was a reading of 0.5 Newton when the object sunk in water. And here we have to say it sinks in water or it's sunk. So now can you all understand the relationship? Whenever the object is completely or partially submerged in water, there was no apparent weight. But when the object sinks in water, there is a certain apparent weight. So from that, you all can understand when the object is partially or completely submerged in water, upthrust is equal to the weight of the object. But when it sinks in water or a liquid, the weight is greater than the upthrust exerted by the liquid. That is the conclusion that we can get from this activity. But with that, when we further do the calculations, you all can get a better understanding about the relationship between the upthrust and the weight of the object at different instances. Okay, students. So you were able to see the activity. You were able to understand how the weight changes or how the weight loss takes place when the object is partially or completely immersed in water. We got all the readings. That is what we need to fill in this table. So tabulate the observations and readings in the table given below. Try to fully submerge the floating object by applying an external force. So here in the first column, you can see objects A, B and C. You can remember A is the object that was partially submerged and floating, B completely submerged and floating, and C is the object that sinks in water. Then weight of the object. So here we got the weight as 1.5 Newton, B was 1.8 Newton and C you can remember it was 2.5 Newton. Then I got the apparent weight of object in water. I introduce this term to you all students, apparent weight. When it is partially or completely submerged in water, the weight that you feel or the weight that you read then, because of the weight loss caused by the upthrust. So you are familiar with all these terms. Apparent weight of object in water. You can remember here it was 0. The second instance also it was 0. The last instance it was 0.5. So only when the object sinks in water you were able to see an apparent weight. In the other two instances the apparent weight was 0. So then, is the object partially submerged and floating, fully submerged and floating, or sunk? First one, partially submerged and floating. Partially submerged and floating. Second one, fully submerged and floating. Fully submerged and floating. Finally, what? It was sunk in water. So, those are the observations that you got. So, what are we supposed to do next? We need to fill in the table that is given in the next slide. It's given in your textbook also. We need to calculate the upthrust as well. So, how do we calculate upthrust? You can remember, students, upthrust is equal to what? Real weight or weight in air, I told you all, minus apparent weight. So, in the first instance, the weight of the object in air or the real weight is 1.5 Newton. Apparent weight is 0. So, what is the upthrust? So, I told you all upthrust, I will write it as A. It is 1.5 minus 0. So, it is also equal to 1.5 Newton. The second instance, upthrust for B. Again, weight of the object in air 1.8 Newton. Apparent weight is 0. So, the upthrust is 1.8 Newton. So, partially floating object, completely immersed and floating object, and the last one, C, upthrust in instance C. The real weight is 2.5 Newton. There was an apparent weight, 0.5 Newton. So, therefore, the upthrust is 2 Newton. Is that okay? In the first two instances, you all can see the weight of the object and the upthrust are equal, 1.5 and 1.5. Here also 1.8 and 1.8. Both instances, the objects are floating. Whether they are partially submerged or fully submerged, it does not matter. They are both floating. So, for the floating objects, you can understand from this itself that the weight of the object is equal to the upthrust, or upthrust is equal to the weight of the object. But when the object is sunk in water, there you can see weight is 2.5 Newton, apparent weight is 0.5 Newton, so the upthrust is only 2 Newton. Upthrust is less than the weight of the object. So, those are the things that you can understand from here. But before we go to the conclusion, again we will fill the table that is given in the next slide. So, here fill the following table with relevant calculations. I did the calculations before, we need to fill it up here. So, first column object A, B and C. Then second one, how the object appeared in water. First one, partially submerged and floating. Partially submerged, and floating. Then second one, fully submerged and floating. Third one, the object is sunk in water. Then we calculated we got the weight. We measured the weight of the object. First one you can remember, it is 1.5 Newton. This is 1.8 Newton and 2.5 Newton. Weight of the object, that is weight of the object in air. Upthrust on the object, that is also 1.5 Newton. This is 1.8 Newton. Here it is only 2.0 Newton. That is why there was an apparent weight. Is that clear to all students? We calculated the upthrust, so using the apparent weight. In the first two instances, there were no reading in the spring balance when the objects were either partially or completely immersed and floating in water. So, the upthrust is equal to the weight of the object. Second instance also same. But in the third one, you were able to see that the weight of the object is 2.5, but the upthrust is only 2 newtons. So, from these students, now you all can understand. Again, if we take the three instances, the object is partially floating. Then there is the weight of the object acting downwards and the upthrust upwards. So then upthrust is equal to weight. That is why apparent weight is 0. Weight equals 0. Why? Upthrust and weight are equal. Difference between those two only gives you the apparent weight. So this is like the equilibrium of forces. Downward force is weight, upward force is upthrust. It is partially immersed and floating on water. Then the second instance. Where you have the object completely submerged and floating in water. There also weight is downwards, the upthrust is upwards, the weight is acting downwards. So here also upthrust is equal to weight. I will put it as A and B so that it's easy for us to compare and see. This is upthrust B and weight of object B. Here also the situation is the same. Upthrust and weight are the same for this particular object. That is why there is no resultant force. So, there is no apparent weight. So, here also apparent weight 0. Now, here students, we calculated the upthrust to be 1.5 Newton. Here the upthrust is 1.8 Newton. So, what can you see there? The upthrust is less. Here the object is partially immersed. Why? The weight of the object is also 1.5 Newton, equal upthrust 1.5 Newton. But when you compare the objects with A and B, A is a lighter object. That's why it's partially immersed or submerged in water. But if you take the second object, the weight is more. Upthrust is also more. That is why it's still floating, but it is completely submerged and floating. So, you have to remember and understand these two concepts. When the object is floating, always the upthrust will be equal to weight. So, for an object that is floating in a fluid, upthrust is equal to the weight of the object. But depending on the object, the amount of upthrust that is exerted by the fluid will vary. So, because of that, the way it gets submerged will vary. Is that clear to you? So, if you have an object that is even more lighter, let's say only 1 Newton, it will be pushed up further. Can you all understand that? The same way, if we use different fluids also, depending on the density of the fluid, the way the objects float will vary. Is that clear to you all? So, from this, you can understand when an object floats in a fluid, partially or completely submerged, upthrust equals weight of the object. And already you all know upthrust is equal to the weight of the fluid that was dispersed. So that is all what you need to remember. That is also equal to weight of the fluid displaced. So that is the Archimedes principle. Upthrust is equal to the weight of the fluid displaced. But when it is floating, that's very important. When the object is floating, upthrust is equal to weight of the object. That's very, very important. So that's the first one, or the first two instances. Then the last instance, or object C. So there what happens, students? Now we had the object. It actually sinks in water. Now here what did we see? The weight acting downwards, that was 2.5 Newton. But the upthrust acting upwards, it was only 2 Newtons. I said you instant C. So here what is the relationship? So here you can see weight is greater than upthrust. So there is a resultant. What is that resultant? That is the apparent weight. And that was equal to 2.5 minus 2.0. We got the value as 0.5 Newton. That is the apparent weight that we read using the spring balance. So now can you all understand the relationship? So here there is a resultant force of 0.5 Newton acting down. So that is why the object goes down. So the weight of the object will be acting on the surface of the container. Is that clear to you all? So when an object sinks in a fluid, the upthrust is less than the weight, or the weight is greater than the upthrust. That is why there is a resultant force acting downwards. That is what we see as the apparent weight. Is that clear to you all? So here, when an object sinks in water, sinks in a fluid, upthrust is less than the weight. So therefore, the apparent weight will act downwards on the surface of the container. So it's going down. Here, of course, it is the container, otherwise the bottom surface. That is why the object rests on the bottom surface. So that is why the object sinks and rests on the bottom surface. So these are the concepts that you need to understand. So we looked at 3 different objects. So these were the calculations that we did from our observations. First 2 instances, the objects were floating. There you saw upthrust equals to the weight of the object. So here I explained that to you all. Again to summarize, instance A and instance B. Here it's partially submerged. There of course it is fully submerged. In both instances, the apparent weight is 0. That means the upthrust is equal to weight of the object. So from that I told you all, we can understand and conclude when an object floats in a fluid, partially or completely submerged, upthrust is equal to weight of the object, but we already know weight of the fluid displaced is equal to upthrust. The same way, if we look at the last instance, where the object sinks in water, there of course weight is greater than upthrust. The difference between the two, weight and upthrust, is what we read as apparent weight. That was just 0.5 Newton, and that is always acting downwards. That's why the object goes down. This is a greater force, this is less force. So there is a resultant force downwards, apparent weight. So therefore, when an object sinks in a fluid, upthrust is less than weight. Therefore, here we can say, therefore, the apparent weight will act downwards on the surface of the container. That is why the object sinks and rests on the bottom of the container. Is that clear to you all? So from this, now you all can understand why different objects float, partially submerged, completely submerged, and sinks in a particular liquid. So that again depends on the object as well as the fluid. Is that clear to you? So with that, students, I will move on to the next slide. So the results obtained from this activity are stated below. What I explained to you all before is given to you here. The weight of the object that was partially submerged while floating and the weight of the object that was fully submerged while floating are equal to the upthrust exerted on the objects by water. So this is one conclusion that you need to understand. The weight of the object that sank in water is greater than the upthrust exerted on the object by water. The second conclusion, this is for the third instance. Object that sank in water. The previous two, the objects that float in water. Is that clear to you? So then we will move on to the next slide. When a force acting vertically downwards is applied on the object A that was partially submerged while floating, an additional force acting vertically upwards can be experienced. So this is same as what I explained to you before. You take a bucket full of water, fill water to a certain extent. It can be complete also. If you just keep a bowl or just a plank of wood and try to push it down, what happens there? It is difficult to push it down. Unless the water flows out, it won't go in. The reason is the water will exert a force upwards. So when you try to push it down, water exerts an additional force so that the object will be in equilibrium. It will be floating as before. So when a force acting vertically downwards is applied on an object that was partially submerged while floating, an additional force, here you have to remember, additional force acting vertically upwards can be experienced. This is because the upthrust is greater than the weight of the object when the object is fully immersed in water, giving rise to a resultant force acting upwards. Therefore, when the external force was removed, the object returns to the original position. That is, the object returns to the position where the upthrust is equal to the weight of the object. I will explain that. It is like this, students. Now you have the same object, but I will show it in two instances. So it is like this. Now here we push the object down. Push the object down and fully submerge it in water. So here what are the forces acting? Now let's say there is the weight plus the force that we exert, that is the push. Already the weight of the object is acting downwards and we push the object down. So push means we apply the force F. So downwards there are two forces, weight and force. You all know when there are two forces, more than one forces acting in the same direction, they get added up. So weight plus force. At the same time there is an upward thrust. What is that? That is the upthrust. So here upthrust is also active. I will say U1. So in this instance, U1 is equal to W plus F. Weight plus the force with which we are pushing the object down. When you release the push, that is what they have told there. Therefore, when the external force was removed. So now let's say we remove the external force. What happens there? The object comes up again. Why is that? The object comes up like that. This is the reason. Now we are not exerting the downward force, only the weight, and there is the upthrust. I will put it as U2. Here also there is equilibrium. The object is still in equilibrium. That means U2 is only equal to W, weight of the object. Here the upthrust was equal to weight plus the external force. That's why it goes down. Earlier also I explained that. You can remember. Instance C, the weight of the object is 1.8 Newton. Upthrust is 1.8 Newton. When it is completely submerged. But the object that was partially submerged, you can remember, weight is less, 1.5 Newton. The upthrust was also less, 1.5 Newton. The same way, here you can see upthrust is only weight. So that is less than upthrust in this instance. Can you all understand now? So it goes up. Now let's say if the weight is even more lesser, I told you all, another object, a very light object, then the upthrust is even more less. The object will be floating further up, less submerged. Is it clear to you? So when you compare the two instances, upthrust 1 is greater than upthrust 2. So if we look at different objects, let's say an object floating like that, an object floating like this, and an object floating like that. Let's say X, Y, and Z. What can you say about the upthrust? In all three instances, upthrust is equal to the weight of the object. Why? All of them are floating. But if you compare the upthrust. Upthrust in instance X, upthrust in instance Y, and upthrust in instance Z. Which is going to be more? This is going to be more. From the previous one, you all can understand that. Now look at the previous one and you all can compare. Here it is like you are pushing it down with an additional force. So the upthrust is also more. So UZ will be greater compared to UY. This instance upthrust is a little bit less. But here you will have the smallest upthrust. Is that clear to you all? So when the object is light, for the same fluid, upthrust will be less and the object will be floating further up. But if the object is more heavier, upthrust is also more, but the object will be completely or almost completely immersed in the fluid. If there was an object that is completely immersed, upthrust will be even more greater. You all can understand that. So based on this only, they have made the hydrometer that we will be discussing at the end of this lesson. So I am sure up to this point you have a very good understanding. Always for an object that is floating in a liquid, in a fluid, upthrust is equal to the weight of the object. And depending on the magnitude of the upthrust, the way the object floats will vary. You all have to understand that. From this, you will be able to compare the upthrust exerted by the same fluid in different objects like these different instances. Is that clear to you all, students? So with that, I will move on to the next slide. So the conclusion that could be drawn from this is that the weight of an object that is partially or fully submerged in a fluid while floating is equal to the upthrust acting on the object, and the weight of the object that is fully sunk in the fluid is greater than the upward thrust. The object sinks in the fluid. So that is what we concluded from the previous activities. So in instance A and B, the objects were floating. So in both instances, upthrust is equal to the weight of the object. But you all can remember, students, in A, the upthrust is less. In B, the upthrust is more. Why is that? In the first instance, when we try to push it down and completely submerge it, we exert an additional force. So there the upthrust is higher. So really the upthrust is higher than the weight of the object, but it adjusts itself so that the object is pushed upwards so that the upthrust becomes equal to the weight of the object. Then in the second instance, where the object was completely immersed, there's no problem, weight is equal to upthrust. And in the third instance, where the object sinks in water or is sunk in water, then the upthrust is less than the weight of the object. So those are the conclusions that you can get from this observation. So here, what are the conclusions? That is, if the upthrust acting on an object completely immersed in a fluid. So when it is completely immersed, it can go right to the bottom of the container. That means it sinks in the fluid. So when it sinks in fluid, when the object is sunk in the fluid, the weight is greater than the upthrust. So if the upthrust acting on an object completely immersed in a fluid is less than the weight of the object, then the object sinks in the fluid. So that is the first instance. So you can remember that here, if I put it in a simple form, it sunk in the fluid, weight and the upward thrust. So up thrust is less than weight. Object sunk in the fluid. Then the second instance is equal to the weight of the object, then the object floats completely submerged in the fluid. What is that? You have an instance where the object is completely submerged. Here the weight is acting downwards, upthrust is upwards, upthrust is equal to weight. So there it is completely submerged in the fluid and it is floating. What is the third instance? That is the instance that we discussed before, where we try to push the object that is partially submerged below the surface of water. So there, what happened? Upthrust is greater than the weight of the object, then the object is pushed upwards so that it floats partially submerged in the fluid and the upthrust exerted by the fluid becomes equal to the weight of the object. Weight of the object. So here what happened? We have the object there. When you have it like this, the weight is down, upthrust is up, but upthrust is greater than weight. So there is a resultant force acting upwards. So here resultant force acts upwards and pushes the object up. So therefore it becomes like this. Now the weight is down, upthrust is up, the upthrust equals the weight of the object. So is it clear now? Even when you have an object like that, what did we discuss? We push the object down. So when you are pushing it down, that means there is an additional force acting downwards, the push, that is equal to the additional upthrust. So there, the upthrust was greater than the weight. Why? Upthrust was equal to weight plus the pushing force. So there, the object, when you release the push, the object adjusts itself so that it becomes like this, partially submerged and floating. There again, upthrust will be equal to weight of the object. So here, object will be partially submerged, and floating. So that is the instance. Is it clear to you all now? 3 instances. In one instance, the object sinks in a fluid. That is the first instance here. So these are the conclusions that we are trying to understand. If the upthrust acting on an object completely immersed in a fluid is less than the weight of the object, then the object sinks in the fluid. So here upthrust is less. So upthrust is less than the weight, object sinks in the fluid. Then what happens? We have an instance where the weight is equal to the upthrust. Upthrust is equal to the weight of the object. Then the object floats completely submerged in the fluid. So here it is like this. Floats completely submerged. And finally, the third instance, where the upthrust is greater than the weight of the object, then the object is pushed upward so that it floats partially submerged in the fluid, and the upthrust exerted by the fluid becomes equal to the weight of the object. So here, when the upthrust is greater than the weight, there is a force acting upwards. It pushes the object up until it floats like this, partially submerged and floating. So there, of course, the upthrust becomes equal to the weight. Upthrust is equal to the weight when the object is partially submerged and floating. So that is why here the upthrust is less than the previous instant. I am sure now you all can understand all these concepts related to floating. The Archimedes principle, when an object is partially or completely submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by the object. And then we saw that in some instances, the weight of the object is equal to the upthrust. Then of course there is no apparent weight. The object shows a reading of 0 weight when it is partially or completely submerged in a fluid. But if the weight is greater, then you will see an apparent weight and also the object sinks in the fluid. So those are the instances that you need to understand. From those, all the conclusions or the observations, the concepts that we understood from the previous activity. So again, as I told you all students, an object sinks or floats partially or completely submerged in a liquid or a fluid depending on the object as well as the fluid. So when we say fluid, you all are familiar with this concept, density of fluids. You have discussed that in your previous grade also. So the density of the fluid can be measured using the hydrometer. And this hydrometer works based on the principle of flotation. That is what I am going to discuss next. So hydrometer. Hydrometers are used to measure the density of liquids and solutions. It is made up of glass. So here it is an instrument used to measure the density of liquids and solutions. You are familiar with different hydrometers. You have discussed different examples also. The soil hydrometer, alcohol hydrometer, lactometers, the normal hydrometers, all that you are familiar with those. And it is made up of glass. It has a cylindrical stem and a bulb as shown in the diagram. The diagram is there in the next slide. Mercury or lead shots are found inside the bulb to enable it to float vertically in the liquid. So, there is mercury or lead shots. So, if I show you all the diagram, a simple diagram. This is how we have a hydrometer. This is the glass tube. Then you have a bulb like that. Inside that there are either lead shots. These are lead shots or mercury. These are metals. Those are usually heavy metals. So, when this becomes heavy, the hydrometer can float vertically up. This helps to float vertically up. The hydrometer vertically up. So, for that this is needed. The liquid or the solution is taken to a vessel and the hydrometer is put into it. So, we will put this hydrometer into a liquid. So, if we put it into a liquid like that, say let's say the liquid level is up to here, the reading will point to this part. So, there is a calibration in the glass tube. So, there you will get the density, value of the density. And usually the density is 0 up and downwards density increases. Why? We have discussed the concept before. When the upthrust is less, the object sinks further. So, there the density of the fluid or the liquid is usually less. If the density of the fluid is less, upthrust is less. So, the object will sink down. So, the density is a lesser value towards the top. But when the density of the liquid is more, it will exert a higher upthrust. So, the object will be pushed up. That is here the hydrometer will be pushed further up. Because of that, the density reading increases when you go down the step. Is that clear to you? The glass tube like that. So, here the concept is based on the density of the liquid. So, here when density of the liquid increases, the upthrust exerted by the liquid increases. Therefore, the hydrometer is pushed up. So, that is how the hydrometer works. This is again based on the concept of flotation. With that, students, we will move on to the next slide. So, here as I told you, the diagram is given. You can see here the lead shots that sealed here with wax. Then you have the scale, the glass stem and the bulb are shown there. This is how you put it into a liquid. You take liquid into a long glass tube and put the hydrometer into it. Hydrometer has been made in accordance with the Archimedes principle. That is what I explained before. In accordance with the Archimedes principle. The hydrometer immerses in the liquid to a height so as to displace a weight equal to the weight of the hydrometer. So, the hydrometer has a weight, upthrust is equal to the weight of the object. So, it has to displace that amount of liquid. the volume of the liquid or the solution displaced is equal to the volume of the immersed part of the hydrometer. So, if it needs to exert a higher upthrust, it has to displace more water. So, the volume of water that has been displaced will be more, the hydrometer will go down more. As a small volume of the liquid is displaced in a high density liquid, the hydrometer is immersed to only small depth. But when it is put in a low density liquid, it immerses more because more liquid should displace to produce the upthrust required to balance it. Is that clear to you all students? So when it sinks more, the upthrust is less. More fluid has to be displaced. So the density of the fluid is less. So from there, so that is how the hydrometer functions. So students, before I explain further, we will go to the lab and observe a hydrometer. Okay students, so now we are going to observe how the hydrometer functions. You all are familiar with hydrometers. We learned this in the previous grade also, and I explained the function as well. So here you all can see the hydrometer, universal hydrometer, that is written here. And then you can see it's a glass tube with calibration, and at the bottom you all can see the lead pebbles or lead shellings, that is to give a weight to this hydrometer, and it has been sealed and contained within this area, and you all know why this part has to be thin, so that you can put it into any thin container containing a liquid. So why do we use this hydrometer? We use a hydrometer to measure the density of liquids. So that is what is calibrated here. Now look at the calibration at the top, it's 0.7. But as you go down, you can see at this point it's 2. So that means the density is increasing as we go down in the calibration in the scale. So how does this function? What is the relationship between the hydrometer and the principle of flotation? When you put an object into a liquid, the liquid exerts an upthrust. Due to the upthrust, you all can remember the objects are pushed upwards. Then they can be submerged at different levels and float in water. So that principle is used to measure the densities. Now when a liquid is less dense, the upthrust it exerts is less. And when the density of the liquid is high, the upthrust is more. So then what will happen is, in a less denser liquid, the hydrometer will go down. Whereas in a more denser liquid, the hydrometer will be pushed upwards. We will look at the reading in water. Here I have water. You all can see the density. What is the value? 1 gram per centimeter cube or 1000 kilograms per decimeter cube. That is the value you can see there. 1 gram per centimeter cube. So that the density of water 1 gram per centimeter cube. That you all know. So in water it is floating at this particular level. If the liquid was more denser, the hydrometer will be pushed up. Then you will get a higher reading. If the liquid is less denser, hydrometer will sink in. We have discussed that before also. So then you will get a lesser reading. So this hydrometer functions based on the principle of flotation. Okay students. So you all saw the hydrometer. You were able to see the lead shots. You saw the scale and you all know how to use the hydrometer. We put it into a container, normally a long jar with water or any fluid, and you can get the reading, that is the density of the fluid. So that is how we use the hydrometer. Now again, going back to the relationship of hydrometer with the Archimedes principle. Now if we have an instance like that, 3 instances we will consider. So then so if we take three instances, liquid A, B and C. So here you can see the hydrometer has been pushed way up. So there, of course, the upthrust exerted by the fluid is greater. You can remember that. So in order to make the upthrust equal to the weight, the object is pushed upwards. That is why it floats only partially submerged in the fluid. So here, of course, the upthrust is less. Upthrust A, here upthrust B and upthrust C. So now students, if we compare the upthrust exerted in these three instances. Now you all know upthrust will be equal to the weight of the object. That is why they are all partially submerged and floating. Whenever they are partially submerged and floating, the upthrust is equal. So in all three instances, the upthrust is equal. And that is equal to weight of the hydrometer. So then, why are they floating in different ways? That depends on the density of the fluid. That is how we relate it with the Archimedes principle. Or the hydrometer has a relationship to the Archimedes principle, and we are able to use it to measure the density of liquids and solutions. We'll see how. Now let's say upthrust is equal. So the weight of the hydrometer is the same. So that means the weight of the fluid that has been displaced has to be equal to the upthrust. So this will be equal to weight of the fluid displaced by the hydrometer. So that is also equal. But then again, that particular weight is given by the volume of the fluid that has been displaced. So here the volumes are different. So that is what we need to understand. So then if we consider the relationship, we can say weight of the fluid displaced is proportional to the volume of the fluid displaced. Why? You all know the equation, students. What is density? Density mass over volume. So here if you want to get the weight is again related to mass into gravitational acceleration is weight. So there, if you want to have the mass constant, then what happens? Density is inversely proportional to volume. So there you get the relationship. Density inversely proportional to volume. So in all three instances, volume of fluid displaced if you look at the diagrams that I showed you all before, here you can see this is way above. This is somewhat in the middle. In C, the hydrometer has gone down. So that displaces more fluid or more liquid. So if we consider the volume of the fluid displaced, there of course A is less, B is a little bit greater, and C is more volume. That means, as I told you here, volume is inversely proportional to density. So density of liquids, there if you compare, A has a higher density than B, which in turn has a higher density than C. Is it clear to you all now? So from the Archimedes principle, upthrust is equal to the weight of the fluid that is displaced. So here the weight of the fluid that is displaced has to be the same, because that has to be equal to the weight of the hydrometer. So in all three instances, upthrust is the same. But in order to provide the same upthrust, different volumes of the fluid are displaced. The reason is the density of the liquids are different. When the density is less, it has to displace more fluid in order to exert the upthrust. When the density is high, it needs to displace only a small volume of liquid so that it can exert the upthrust. So this is the relationship. Upthrust is the same, volume of the fluid displaced increases this way, therefore density decreases. If the density of the liquid is less, the object has to displace more liquid. So that is how we use the hydrometer based on the Archimedes principle. So I am sure you all can understand that concept. So in this particular diagram, if we consider the densities, the density of C is less, density of B is a little bit more, and the density of A is the highest in these three instances. So that is how we use the hydrometer. And with that, students, I have come to the end of this lesson. So I will be discussing the summary in the next slide. Summary: pressure is produced by liquids and gases as well as by solids. So pressure is exerted by all three states: solids, liquids and gases. So normally for solids, we define the pressure as force exerted over a unit area. That is due to the weight of the object. It exerts a force, a perpendicular force, that divided by the unit area or the surface area is the pressure. Then if you take the pressure due to a liquid, it acts in every direction. Normally the pressure of a liquid column is exerted on the bottom surface of the container, but still it acts in all directions. The pressure due to a liquid increases as the depth or the height of a column of liquid increases. So you all know when the height of the column is greater, the pressure exerted is more. When the height of the liquid column is less, the pressure exerted is less. Or as the depth increases, the pressure increases. Then the formula P equals H rho G is used to find the pressure due to a liquid column, where H is the height of the liquid column, P is the density of the liquid column, P or it can be rho. P or rho is the density of the liquid column, G gravitational acceleration, that also you all know. So rho here is the density. Depending on the liquid, the pressure exerted varies. And depending on the height also, the pressure exerted varies. The space around the earth containing air is known as the atmosphere, and the pressure produced by atmospheric air is known as the atmospheric pressure. So we discussed that also, atmospheric pressure. And you all can remember, students, atmospheric pressure decreases as we go to higher altitudes. And normally at the mean sea level, it is 76 centimeter mercury when we use the mercury barometer. And Mount Everest, you all can remember, it's about 25 centimeter mercury, very much less. The average value of the atmospheric pressure at the sea level is 76 centimeter mercury. You have to remember that. That is, the atmospheric pressure at the sea level is equal to the pressure due to a mercury column of height 76 centimeters. You have to always take the vertical height. You can remember that. In order to measure average value of the pressure, the mercury barometer and the aneroid barometer are used. Mercury barometer has mercury, aneroid barometer, there are no liquids in that. When an object is partially or completely submerged in a liquid, an upthrust equal to the weight of the quantity of liquid displaced acts on the object by the liquid. So this is when an object is partially or completely submerged in a liquid. There is an upthrust acting on it that is equal to the weight of the quantity of liquid displaced. That is what we discussed as the Archimedes principle. Again, to recall the Archimedes principle. When an object is partially or completely submerged in a fluid, the upthrust exerted by the fluid is equal to the weight of the fluid displaced by that object. That is the Archimedes principle. And finally, when an object is floating on a liquid, the weight of the displaced liquid is equal to the weight of the object. So when an object is floating on a liquid, it can be partially or completely submerged. The weight of the liquid displaced is equal to the weight of the object. So that means the upthrust is equal to the weight of the object. There is no resultant force. There is no apparent weight. You all can remember that. So this is the summary of this lesson. We started off by discussing the pressure exerted by solids. Then we moved on to pressure exerted by liquids and we did calculations. Then transmission of pressure through liquids. We discussed the hydraulic hoist, the hydraulic press, then the hydraulic jack, hydraulic brake systems, all based on the concept of hydraulic press. Then thereafter, we discussed the pressure exerted by gases, atmospheric pressure, and the instruments, that is the mercury barometer and the aneroid barometer, and also the applications or uses of atmospheric pressure in day-to-day life. And finally, we discussed the concept of flotation, where we understood what upthrust is, and also the Archimedes principle, and then the way different objects float or sink in fluids, and finally the hydrometer and how the Archimedes principle is utilized in the hydrometer in order to measure the density of liquids. So those are all the concepts that were discussed in this lesson. I am sure you all have a good understanding of those. In the next chapter, I will discuss the questions given in your textbook and thereafter some extra questions as well.